Okay, hi everybody. This is topic 3 for AP Calc AB, and the topic notes start on about page 11. So we are looking at determining intervals on which the function is increasing and decreasing. And the essential question is, how can I use the derivative to accomplish that? And so when we look at the idea of increasing and decreasing, I'm just going to use this graph down here as an example. This is the derivative. Pretend that this is the actual function. So we have increasing, decreasing, increasing, decreasing, right? Increasing, right? So increasing on an interval I occurs when the derivative is positive, and decreasing on an interval I is when the derivative is negative. So if we don't actually have the function, then we can use the derivative and still make those same conclusions. So when we look at this question here, so this is kind of a common theme in Unit 5, that a lot of times we don't have the function, we just have the derivative. And a lot of times they give us a graph, and you got to be really cognizant of what you're looking at. So that they like to give you the graph of the derivative values. So so we use this not knowing what the original function is, and we say, okay, well, if this is the derivative, then I need to know where the derivative is positive. And of course, this horizontal axis here is going to divide the positive values from the negative values, right? We're looking on the y-axis now. So the derivative is positive here and here and here and here. Okay, it stays above that horizontal axis. And the derivative is negative from 3 to 5. And so if we have the graph of the derivative and from this interval from -2 to 5, and we want to know where the function itself is increasing, we're going to look at this positive location here. So with this graph of f prime, and notice I labeled the axis here, there's a lot we can tell from this graph of the derivative. We can tell that we have critical points at -2 and 1 and 3 and 5. Remember, the critical points are where the derivative is either 0 or undefined. And there are no undefined derivative values in this interval, but there are critical points because we have some 0 values there. And really, we're going to have this reoccurring theme in Unit 5 of finding those critical points algebraically if we do know the function. So this function f is increasing then. This function is increasing then. Clicking is not working. There we go. From -2 all the way out to +3. So when we look at these answer options, -2 to 1. The function's increasing, but that's not the entire interval, right? It's only kind of a partial answer. And 0 to 1.5 doesn't really make that much sense, and certainly 3 to 5 doesn't make that much sense either. And of course and E doesn't make that much sense either. So A could be a good distractor, but it doesn't represent the entire interval over which the function is increasing, so it's not the correct answer. So in finding increasing and decreasing intervals, like I said, we're going to follow this common theme of finding the critical points. And you can go back and see that on what would that be? That would be topic 2. We had the steps to do that: finding the derivative, setting it equal to 0, looking for where it's undefined, those sort of things. And then what we're going to do is we're going to sketch a number line to include all the critical points. So this number line is going to be a derivative number line. And then we're going to annotate that number line by picking x values between the critical points, so that we can put that into the derivative and see what the value of the derivative is, if it's positive or negative. And then we'll examine that whole number line and we'll make our justification. So let's do that on this example here. It says let f be a function with the derivative given by f prime equals x squared minus 2 over x, on which of the following intervals is f decreasing. And so in this case, there's no restriction in the domain. We're going from negative infinity to positive infinity. And so we already have the derivative. There's no differentiation involved. So, but we do need to find the critical points. And so, and then we're going to look, after we test each interval, we're going to look for where the derivative is negative. So we know the derivative is as it's stated. We're going to set it equal to 0. We're going to solve this. So the best way to solve this is I'm going to move the rational portion over to the right, and I'm going to cross multiply. So I'm going to x cubed equals 2. And so x equals the cubed root of 2, which you notice is present in some of those answers. And so I'm going to draw, and then, oh yeah, and then I'm going to look at where the derivative doesn't exist, right? Because this expression has a rational component to it. And where does it not exist? It doesn't exist when x equals 0. So again, we're looking at derivative values. And if I would graph this at x equals 0, we would get a non-finite value. So we know that our derivative doesn't exist at x equals 0. So we've found the critical points. We have a critical point here at the cubed root of 2, and we have a critical point at 0. And so now we're going to make our derivative number line. And we're going to note where we have 0. We're going to note our critical points. So the cubed root of 2, I'm not quite sure where that is, but I know it's bigger than 1. And I know it's less than 2 because this would be the cubed root of 8. And this is the cubed root of 1. So we're just beyond 1 here. And then, of course, we have an undefined derivative. That's what I mean by u at 0. So those are our critical points. And now that creates 3 intervals: the interval here, the interval between, and the interval here. And so we need to test in those intervals. And we need to pick a convenient point to test. So like -1 is convenient. So I'm going to put -1 into the expression of the derivative. And so I'm going to get 1 plus 2, that's 3, and it's positive. Notice I don't even put a 3 there because I'm just looking at this for positive or negative. So I'm not even really simplifying it at all. I just know that this is positive minus a negative is positive, positive plus a positive is positive. That's how I'm looking at that. And now I'm going to test 1 because that's between the undefined and the 0 critical points. And when I put 1 in here, I get a negative value, right? I get 1 minus 2. I get a -1. So I'm looking at that. It's just a negative value. And then when I test out here, it looks like I'm going to test at 2 here. And so I put 2 into the expression. I'm going to get 4 minus 1. That's 3. That's positive. So I have that. So now I'm using this number line to as an organizer so that I can make my justification. My justification is I want to know where the derivative is negative, and the derivative is negative between the critical points. So it's going to start at 0 and go to the cubed root of 2. So that means the answer is D. For question 3, it says, now I have the function. So this is what I kind of alluded to earlier, but you really got to know what you're looking at. So now I have the function, and I'm being asked, it's basically the same question. On which of the following intervals is the function decreasing? There's no restriction on domain, so I'm going from negative infinity to positive infinity. So the first thing I need to do then is acknowledge, I'm just going to make a little note here on my organizer that I'm looking for a negative derivative. So I need the derivative. So I'm going to go ahead and differentiate this, which is 300 minus 3x squared. And I'm going to set it equal to 0. And I'm going to go ahead and algebraically solve that. Now, I am choosing to factor this, it looks like. Does that make sense? I'm factoring a quadratic. There are other ways to solve that. But factoring it really points out the fact that there are 2 zeros. I can a positive 10 and a negative 10 that make the expression for the derivative 0. The other way to solve this is to kind of use a square root method. And then you just got to remember to take out that plus minus sort of solution option if you do that. So on my derivative number line, and another component is that we really want to see this number line on free response questions, and we want you to label it as the derivative number line. So you should have an F prime or something like that. And that helps the justification process. Okay, so I'm going to put my critical points here. It looks like I've got a critical point way over here and a critical point way over here. And this derivative is quadratic. So itself is a function. So we know that a quadratic function doesn't have any undefined values, and doesn't have any values of x for which the function is undefined. And that'll be true for polynomials, that, we won't have any undefined derivatives. So I don't have to worry about saying anything about f prime being undefined. It's just not possible. And they expect you to know that based on the fact that they gave you a polynomial. So I'm going to test 11 out here, negative 11, excuse me, misspoke. I'm going to test negative 11. So I'm going to put negative 11 into this expression of the derivative, 3 times the quantity 100 minus x squared. And of course, squaring negative 11 makes it positive. 100 minus, I know this is bigger than 100, so this whole thing is negative. So I'm just going to put a negative sign there. Again, I'm not going to simplify it. I'm just looking at 100 minus a number, minus 121, right? It's going to end up being a negative value. I'm going to test 0 because it's super easy to test. I'm going to put 0 into this expression. And so that's positive. And then I'm going to put positive 11 as a test. I try to make this symmetrical whenever I can, because it leads to really similar results. This is also going to be negative. So to answer the question, that the function is decreasing when the derivative is negative, that's going to start at negative infinity and come up here to 10. And then it's going to start at 10 and go out to positive infinity. So I have 2 intervals where the function is decreasing. And so the answer here is A. Now, in terms of the use of square brackets or rounded brackets, and the debate on whether or not to include 10, since 10 is a critical point technically, they really are not that specific. Like if this were a free response question, you put square brackets here, they would mark it. You'd get the answer point. And if you put rounded brackets here, you'd still get the answer point. They're not that specific about whether or not to use square or round brackets. The only thing they're specific about is that infinite values should always have round brackets. So that is that question. Okay, so this next question, it says, let y be the function g of x. And it's differentiable and increasing for all real numbers. So think about g of x being always increasing, right? Never decreasing. Meaning the derivative or the slope of the tangent lines of g of x is they're always positive values. That's kind of the information you get out of that. So it could be like g of x is exponential, right? Exponential is always increasing. Could be something like that. We just don't know. But what we're going to do is we're going to use g of x, and then we're going to put in this cubic. So we're going to need the chain rule. We have a composite function being generated here. So I wouldn't have called it y again, but I'm not going to change the stem of the problem. They're saying y is g of x cubed minus 6x squared. So it's that composite. And we want to know where it's increasing. So we want to know where its derivative is positive. And so this is what helps us with the idea of g of x being differentiable and increasing for all real numbers. So we know we can differentiate this because they said it was differentiable. And we know it's continuous because all differentiable functions are continuous. So I'm going to go ahead and differentiate this. So I'm going to differentiate the outside, call it g prime, leave the inside by itself, and then times the derivative of the inside. And I'm going to set that equal to 0. We also know that g prime is always positive, right? That's what this means. And so what we have then is this component is always positive. So really, I just need to set this component equal to 0, because a positive times anything you have here is going to be whatever this sign is over here. So as I factor this and I solve this, I get critical points at x equals 0 and x equals 4. I couldn't set the original expression equal to 0 because there's no way of knowing where this is 0. But it doesn't matter because we know its derivative is always positive. So when we set up our number line here, we're going to have our critical points at 0 and 4. And then we're going to just treat this like we've treated every other problem. We're going to pick a point to test. So I'm going to pick -1. I'm going to put -1 into this expression. And I just need to worry about, I guess I put it into the factored expression here. I just need to worry about this expression because this is always positive. So I have 3 times -1 times -5. So this is a positive times a positive, that's positive. And then I'm going to try positive, let's see, the next one I'm testing is +1. So I'll put a +1 in here. And it looks like I've got a negative value, but a negative times positive is still a negative value. So we're good there. And then we're testing 5 here. On the other side of the critical point, when I put in 5, I get a positive. Positive times a positive is a positive. So where is the function increasing? It looks like it's increasing on the left-hand side from 0, or from -infinity to 0. And then again from 4 out to +infinity. So this one looks like the answer is A as well. Okay, and we will do the takeaways when we get into class, next class period.